This is Felix Zemdex, a professional speed cuber, and he's about to get the, at the time, world record for the fastest solving time for the 3x3 Rubik's Cube. Except his record is nowhere to be found in the archives. This is because Felix got what's known as a corner twist, which caused his record to be rejected. But why is a corner twist problematic in the first place? Can't he just fix it? Well, if you're familiar with solving the Rubik's Cube, you might know that a corner twist is unsolvable. No matter how much you twist or turn the cube, the corner twist will never get corrected using legal moves. This is a very well-known fact among the speed cubing community. However, what's far less known is the reason why we know for sure, in fact with mathematical certainty, that a corner twist is impossible to solve. In this video, we will use group theory to prove that a corner twist is unsolvable, and get a visual way to determine whether a given configuration is solvable or not. The Rubik's Cube is a combination puzzle invented by Erno Rubik in the 1970s. It consists of 26 pieces, 8 of which are corner pieces containing 3 colors, 12 are edge pieces containing 2 colors, and the remaining 6 are center pieces, also called cores, which contain 1 color. To make our study easier, we will adopt certain conventions, the first of which is fixing an orientation for the Rubik's Cube, which is done by naming each face of the cube based on its position to an observer. So we'll take the green face to be the front face and the white face to be the up face. This makes red the right face, orange the left face, yellow the down face, and blue the back face. All of these names will be abbreviated to R, U, D, L, F, B. The next useful convention is to give names to the individual pieces, which uses the face names already established. A corner piece is named by concatenating the letters of the faces it's adjacent to. For example, this piece would be called URF. The concatenation is not done in any particular order. The same is done for the edge pieces, except the name of an edge piece contains only 2 letters. Thus, this piece, for example, would be called LF. Another useful convention is to give names to the space a piece occupies, which we call cubicles. A cubicle is named after the piece occupying it when the cube is in its solved state. Note that cubicles do not change position when applying moves to the cube. Applying this turn to the cube moves the DLF piece into the ULF cubicle. We call a configuration any rearrangement and reorientation of the cube's pieces. We can determine the total number of configurations of the Rubik's Cube via a simple combinatorial argument. But not all of these configurations are solvable. We will reduce this number to represent only the solvable configurations at the end of the video. A configuration is said to be solvable if there exists a sequence of moves that, if applied to it, results in the solved state. But what do we exactly mean by a move? We call a move any finite sequence of the 6 basic face turns, where a basic face turn consists of turning a whole face clockwise, and they are, quite clearly, moves themselves. We shall denote each face turn by the letter of the face it turns, indicated by the appropriate centerpiece. But wait, is this naming scheme even well defined? If, for example, we conduct a middle move just like this, the orientation of the cube's faces is all messed up. And, for example, a right turn no longer corresponds to turning the face that's on the right. This is in fact not a problem, and the names are indeed well defined, but we have to wait a little bit to know why that is. Now, by just playing around with the cube, you can notice that the moves satisfy 2 fundamental properties. The first is that moves can be combined to create new moves. Applying 2 moves one after the other and ignoring the separation between them undeniably results in a new move. The second is that any move is reversible, which can be done by reversing the face turns constituting the move in reverse order. If you're familiar with group theory, your sensors should be going off at the mention of these 2 properties. These 2 properties indicate that the moves of the Rubik's Cube have the structure of a group. Well, almost. For those who are unfamiliar, groups are a fundamental structure in mathematics, used to study symmetries and number systems. They are defined as some set, say G, equipped with a binary operation, which is some function that takes 2 elements of the set G and combines them in some way to obtain a new element in G. A group must satisfy the following 4 properties. The first is closure, which says that the combination of 2 elements of the group via the operation must not exit the group. The second is associativity, which states that the way you group elements when combining does not change the final result. The third is the existence of some element of the group that, if combined with any other element, leaves it unchanged. This is called the identity element. And finally, any element has an inverse, which is a unique element that, when combined with the original one, results in the identity. Now, if this sounds really complicated, then do not worry, because today's sponsor Brilliant has got you covered. Brilliant is an engaging and interactive learning app designed to help you reach real learning goals in subjects such as mathematics, computer science, engineering, data science, and more. Its lessons are focused but comprehensive, carefully crafted by award-winning experts to build your reasoning and intuition from the foundations all the way to mastery. Visual learning on Brilliant isn't just a gimmick or a casual pastime. It's a serious tool that can make concepts click faster, supplementing knowledge with problem-solving skills and allowing you to do more with the same amount of effort. We like Brilliant because its bite-sized lessons make learning possible even if you're pressed for time, and its streak system gives you a daily dose of encouragement to help you stay on track, make progress every day, and build your habit of learning. We all have goals, and Brilliant won't just get you started, it will get you there. So don't miss out. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/mathverseanimated or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Thanks once again to Brilliant for sponsoring this video. Going back to the Rubik's Cube, it's obvious that with some little tweaking, we can give the moves a group structure. It is clear that closure and invertibility are already satisfied. By ignoring this separation between conducting moves, we can also assert that associativity is satisfied. It only remains to establish that an identity exists, but that is very simple. We only need to consider doing nothing as a move. Leaving the cube untouched, which corresponds to a sequence of face turns of length 0, can be seen as a move. Hence, we have our identity element. The underlying binary operation that's implicitly assumed here is just ignoring the separation between moves, which we'll denote by arrow. For any two moves, say M and N, M arrow N is just the new move Mn, which is done by executing all the face turns comprising M, then all the face turns comprising N without pauses. An important property the group of moves satisfies is that it's generated by the 6 basic face turns. Formally, a group G is said to be generated by one of its subsets E if all its elements can be written as a finite combination of elements of E and their inverses. And by definition of a move, this is very clearly the case. We'll denote the inverse of the basic face turns with the same letter, but with an apostrophe. This remark is extremely important because making statements about the generators of a group is the same as making that same statement about all the elements of the group under certain conditions. This is expressed in the following proposition, which can be easily proven by induction and is verified by the Rubik's Cube. This makes our work astronomically easier. If we want to check that the cube satisfies a property, then instead of checking it for all the moves, we only need to check it for the 6 basic face turns. In fact, we can already make some pretty strong statements. For example, since no basic face turn changes the positions of the core pieces, then no move changes the position of a core piece, which is why the naming scheme we came up with at the beginning of the video is well defined, and the problem posed by the middle move can be mitigated by conducting the equivalent move of turning the adjacent faces in the opposite direction. Furthermore, since all 6 basic moves switch corners with corners and edges with edges, then all moves can be seen as permutations of the corners and edges which are done independently from each other. This last remark motivates us to try and identify the group of the moves with the more elementary and familiar group of permutations. First, recall that a permutation of n elements is formally defined as any bijections from the set of numbers from 1 to n onto itself. The set of all n permutations is denoted by S sub n and forms a group when equipped with function composition called the symmetric group of order n. A permutation is often expressed when n is relatively small in this matrix notation, where the first row contains the numbers from 1 to n and the second row contains the image of each element under the permutation at hand. Often in permutations, much like the permutation tau on screen, some elements keep looping to each other when repeatedly applying the permutation, forming a cycle. These are in fact sub-permutations occurring within the original permutation and are accordingly called cycles. When these cycles are disjoint, meaning they share no common element, then we may re-express the permutation tau as a product of these cycles. These parentheses are used to separate the cycles, and this notation means that 1 is mapped to 4, 4 is mapped to 3, and 3 is mapped back onto 1. And the same concept is applied to 2, 5. You can easily check that this gives back the original expression for tau. Such an expression is called a disjoint cycle decomposition, and this property is shared by all permutations. In other words, any permutation can be written as a product of disjoint cycles. Of course, what we mean by product is just function composition, Since permutations are nothing but maps, we can actually go further and assert that any cycle can be decomposed into a product of transpositions, where a transposition is a permutation that switches two elements and leaves the rest unchanged. One such way to decompose a cycle into a product of transpositions is what you see on screen right now. Try to see why this holds. All of this means that any permutation can be decomposed into a product of transpositions. Such a decomposition is not unique. In fact, infinitely many such decompositions exist. However, what's shared between all decompositions is their parity, meaning if one decomposition of a permutation into transpositions contains an even number of terms, then all decompositions will contain an even number of terms. This allows us to classify all permutations into two classes, even permutations and odd permutations. We consequently define the signature of a permutation to be the quantity minus 1 to the number of transpositions. We say a permutation is even if it has a signature of 1, and odd if it has a signature of minus 1. Let's apply all of this to the Rubik's Cube. We must first agree that any move, say m, induces a permutation of the cube's pieces, which we'll denote by sigma brackets m. Since corners and edges are not mapped onto each other, it stands to reason that we may write sigma brackets m as a disjoint product of the corner permutations and edge permutations, respectively denoted sigma sub c brackets m and sigma sub e brackets m. These permutations can of course be decomposed into cycles and by extension transpositions. Let's take a practical example and see how this works. Let's see what these permutations look like when conducting a right face turn. Remark that the DRF corner is sent to the URF cubicle. The URF corner is sent to the URB cubicle. URB is sent to DRB and DRB is sent to DRF. We've got ourselves a cycle, in fact a 4 cycle as it contains 4 elements. You can try and do the same work with the other moves to see that all 6 basic face turns are nothing but 4 cycles not only for the corners but for the edges too. A more complex example would be this heavily used move in algorithms, given by RU, R', U'. You can in fact check that its induced permutations can be written as follows. This of course can be further decomposed into a product of transpositions. And so for any configuration we may describe the placement of the corner pieces as a permutation belonging to S8, and the placement of the edges is described by a permutation of S12. In other words, the permutation of the pieces for any move may be seen as an element of S8 cross S12. This is brilliant so far. We have reduced the placement of the pieces of the Rubik's Cube to 2 permutations in S8 and S12, whose structures are well understood. Now, consider these 2 configurations, which are visibly distinct. Yet, with the tools we've developed so far, there's actually no way of distinguishing between them. This is because although the placement of the pieces is the same, meaning these 2 configurations have the same induced permutation, that being the identity, what's different is the orientation of this corner piece. This is because representing a configuration as an element of S8 cross S12 does not take into account the orientation of the pieces, only their placement, so it does not cover all of the configurations of the Rubik's Cube. We need more tools to describe the orientation of the pieces. Observe that the corner pieces have 3 possible orientations and the edge pieces have 2 possible orientations. This motivates us to assign a number to the orientation of a corner piece ranging from 0 to 2 and a number to the orientation of an edge piece ranging from 0 to 1. To properly do this, we're going to adopt the following convention. If you have a spare Rubik's Cube, I suggest you get an erasable marker, we don't want you to ruin your cube, or some stickers and follow along with this procedure. Let's consider the solved configuration of the cube, and let's adopt the orientation of the cube we fixed at the beginning. We will number each corner piece from 1 to 8, and we will write the number on the up face if the piece is an upper piece, and on the down face if it's a lower piece. Start from the URF piece and write the number 1 on its up face. Then going around counterclockwise, write the next number on the up face of each corner piece until you reach the UFL piece, which should have the number 4 written on it. Now flip the cube over. Starting from the DFL piece and on the bottom face, write down the number 5. And go around the cube again counterclockwise, marking each piece in ascending order. You should have the number 8 written on the DFR piece. Now for each piece, do the following. On the face that has a number written on it, either replace the number written with or just write down the number 0. Then going around the piece clockwise this time, start marking each face of the piece in increasing order, 0, then 1, then 2. Doing this for all the corner pieces, your cube should look like this. What we have essentially done is assign to each configuration of the cube a ternary 8 tuple, where the ith entry takes the number that's written on the up face of the ith corner piece. So in summary, the indices 1 to 8 indicate the cubicles, and the numbers 0 to 2 give the orientation of the piece in each cubicle. We will do this same work for the edge pieces, but for the sake of brevity, we'll summarize these steps to follow in this table. After you finish writing these numbers, mark down a 0 on the face containing the number and a 1 on the other face. So finally, your cube should look like this. This was a lot of work and maybe a bit confusing, but this naming scheme will finally allow us to give a formal characterization for a configuration. A configuration is uniquely determined by 4 things: its permutation of the corner pieces in S8, its permutation of the edge pieces in S12, the orientation of the corner pieces described by a ternary 8 tuple, and finally the orientation of the edge pieces described by a binary 12 tuple. Symbolically, if we let C denote the set of configurations of the Rubik's cube, then any one of its elements, i.e. a configuration in C, can be written as a 4 tuple, each entry containing one of the 4 objects characterizing a configuration in order. Hence, we can see the set of configurations as a subset of the Cartesian product of the 4 sets characterizing each attribute of a configuration. You may observe in particular that the solved state can be written per this formalism as follows. Of course, the zeros here abusively denote the 0 tuples. Let's take a step back and see what we've got so far. We've got the group of the moves, which represents the abstract motions that can be applied to the cube on one hand, and on the other hand, we've got the set of configurations, which is mathematically structureless. The group of the moves behaves like a stickerless Rubik's cube, where you can apply the moves all you want, but nothing changes. And each configuration in C behaves like a cube without any mechanism inside or moving parts. In order to finish our mathematical model and obtain a playable Rubik's cube, we must set up a link between the group of the moves and the set of configurations. The tool that's going to achieve this is group actions. The action of a group G on some set S is a mapping from S cross G to S, which satisfies these 2 properties. Now, explaining the intuition behind how group actions behave and what purpose they serve is a bit beyond the scope of our topic. But for ease of mind, you can notice that the Rubik's cube on its own cannot jump from a configuration to another. It may only be acted on by, say, your hand. Hence, you may interpret the group action as the hand that is applying the moves to the Rubik's cube, abiding by the rules of group theory. This specific action is defined as the map which assigns to any pair of configuration and move, say Cm, a new configuration C', which is obtained by applying the move M when the cube is in the configuration C. Of course, it is easy to determine the permutations and orientations characterizing the configuration C' based off of those characterizing C. From each configuration, a special set can be obtained, called its orbit, which is defined as the set of all possible actions on said configuration. The key property about orbits is that they partition the set the group acts on. More precisely, any configuration of the cube can be in one and only one orbit, and any one of the elements belonging to the orbit may be taken as its representative. In our case, an orbit of some configuration is the set of all possible configurations that can be obtained by applying all possible moves to it. This is huge. Recall the definition of a solvable configuration. It's any configuration that can be reduced to this solved state by applying some move M to it. But this means that a configuration is solvable if and only if it's in the orbit of the solved state. In other words, the set of solvable configurations is precisely the orbit of the solved state. It's very serendipitous that orbits verify a similar proposition to the one introduced earlier. That is, properties are shared between elements of the orbit. This assertion is formally described by the following proposition. It's not too difficult to prove this proposition using the previous one. What matters is that, as per this assertion, making a statement about a representative of some orbit is the same as making that same statement on the entirety of that orbit, of course, under certain conditions. So, if you can extrapolate properties from the representative of the solvable configuration set, which is the solved state, then we can obtain characterizations for any solvable configuration. We're finally going to employ all the tools we've developed so far to prove this theorem called the fundamental theorem of the Rubik's cube, which states that a configuration is solvable if the signatures of its permutations are equal, the sum of the components of its corner orientation is congruent to 0 modulo 3, and the same holds for the edge pieces except modulo 2. The proof of this theorem is split into 2 lemmas. The first deals with the permutations and the second deals with the orientations. We will prove both of these lemmas. The first lemma states that if two configurations share an orbit, then the product of the signatures of their permutations must be equal. First, observe that since these two configurations are in the same orbit, then there must exist some move M such that C' is equal to the action of M on C. This would mean that the permutations of C' is equal to the composition of the permutation induced by M and the permutation of C. You can check that it follows that the signatures also equate, and we may multiply these two equations term by term. If we can show that the signatures of the permutations induced by M multiply to 1, then we would be done. Similar to what we've established earlier about the right face turn, any basic move can be expressed as a 4 cycle for the corners and the edges. It follows that the corner and edge permutations have a signature of -1. If B1 through Bn is the sequence of basic moves which make up M, then we must have that the permutations induced by M are just the product of the permutations of each basic face turn. This of course means that the signature of both of these permutations is the product of signatures of the permutations induced by the basic face turns. We're going to pick up a -1 from each term in this product because again each term is a 4 cycle. Note that we have the same exponent here because there are as many edge permutations as there are corner permutations for any basic face turn, which is not too difficult to see. Multiplying these two signatures gives our desired result. Now immediately, since the permutations associated with this solved state are both the respective identities of S8 and S12, both of signature 1, we get the first part of our theorem. This lemma eliminates the cases where two pieces have switched places without switching the orientations. The second lemma states that if two configurations share an orbit, then the sum of the corner orientation components for both configurations are congruent modulo 3, and the sum of the edge orientation components for both configurations are congruent modulo 2. This lemma will be demonstrated exhaustively in the sense that we'll check the effect of each basic face turn on the orientation of the pieces it affects, and verify that the contributions to each component sum to 0, modulo 3 and 2 respectively. So without loss of generality, we may assume that C and C' are in the same orbit, with C' being equal to C circle M, where M is a basic face turn. M can be any move, but checking for basic face turn suffices. Let C1 through C8 be the corner orientation of C, and E1 through E12 be the edge orientation of C. We'll summarize how each face turn affects the orientation of C in the following table. You can see for example that the U and D turns do not change the orientation of any piece, which can be confirmed visually. In the case where an orientation change occurs, you can check that the contribution is always equal to 6 for the corners, which is congruent to 0 modulo 3, and equal to 4 for the edges, which is 0 modulo 2. So regardless of the move applied, the remainder is always preserved modulo 3 for the corners and modulo 2 for the edges. Now in particular, since the solved state's orientations consist of the 0 tuples, it follows, according to this lemma, that any solvable configuration has a corner orientation whose components sum to 0 modulo 3, and has an edge orientation whose components sum to 0 modulo 2. And that's it, the fundamental theorem of the Rubik's Cube is proved. Well, I lied. The fundamental theorem of the Rubik's Cube is actually an if and only if statement and not just an implication, but we've chosen to omit the second implication to avoid the video being too long. But what we've just proven is enough to see why a corner twist is unsolvable. If you consider any corner twist, take the orientation tuple and sum the components, you'll find that the sum is either 1 or 2, which is in 0 modulo 3, and so a corner twist cannot be solved using any legal moves. In fact, for any configuration, as long as it's solvable, you'll notice that the sum of the numbers shown on the up and down side of the corner pieces always sum to some number that's 0 modulo 3. This theorem also tells us that the edge twists are also unsolvable, but such cases practically never occur when speed solving. Here's a fun simple exercise. Can you tell why two corner twists in the same direction are unsolvable, but two corner twists in opposite directions are? Finally, we can determine the number of all solvable configurations. We'll start from the first number we found earlier in the video and shave off all undesirable properties which render a configuration unsolvable. First, since the signatures of the permutations must be equal, i.e. their product must have an even signature, this already removes half of the configurations, as there are only two possible signatures. Next, for a configuration to be solvable, it must lie in only one of the 3 orbits generated by each corner twist, the one which corresponds to the remainder of 0 modulo 3, and so another third of the configurations is gone. For the same reason, the edges only have 2 orbits of their own, so to eliminate the edge twists, we divide by 2 again, to get this final result. For reference, 43 quintillion sheets of A4 paper stacked on top of each other would cover the distance from Earth to Pluto over 700 times. The Rubik's Cube still hides a lot of mathematical applications to explore, from how commutators and conjugators are used to find algorithms solving the cube, or how to optimize the number of moves used to solve the cube with as little turns as possible. People have even tried to solve the cube while taking into account the orientation of the core pieces. And this is only concerning the 3x3 cube. There are many shapes and sizes that can be analyzed and explored. So if you would like to see any of that, please let us know in the comments below. We thank you so much for your support and we hope you've enjoyed this video. Thanks for watching.